Professor Rao Li from USA. He will deliver the lecture. So now I am hand over the session to Professor Narasimha to continue the process.
Yeah,
Sir,
Prof. Thank you.
sir,
Thank you
can
very
you
much.
introduce the speaker and then the speaker will start
Yeah,
the lecture.
yeah. It's a great privilege. I thank the opportunity given to me to chair the session. And prior to this, let me introduce Professor Rao Leo, who is going to deliver his talk on the degree-based indices, classical inequalities, and some Hamiltonian properties of graphs. Professor Liu is in the Department of Computer Science, Engineering, and Mathematics at the University of South Carolina, USA. He acquired his PhD in Mathematical Science, specializing in graph theory, and his MSc in Mathematical Science, specializing in computer science, simultaneously from the University of Maryland, USA in May 1999. A strong academic background in both mathematics and computer science has enabled him to make significant contribution to this interconnected discipline throughout his career. Following the completion of his graduate studies, Professor Lee began his academic career as an assistant professor in the School of Computer and Information Science at Georgia Southwestern State University, where he served from August 1999 to May 2001. In the fall of 2001, he joined University of South Carolina, Aiken, where he has continued to contribute to teaching, research, and academic development as a faculty member in the Department of Computer Science, Engineering, and Mathematics. As a distinguished graph theorist, Professor Liu's research encompasses several important areas of graph theory, including Hamiltonian graph theory, spectral graph theory, and topological indices of graphs. His work has advanced the theoretical understanding of graph structures and their mathematical properties, contributing significantly to the field of discrete mathematics. In parallel, as a computer scientist, he actively conducts research on the design and analysis of algorithms, bridging mathematical theory with computational applications and addressing complex problems in computer science. Further, Professor Liu has maintained an outstanding record of scholarly productivity, having authored and co-authored more than 160 research articles covering graph theory, algorithms, and related areas of mathematics and computer science. His extensive publication record reflects his sustained commitment to advancing research and fostering innovation in both theoretical and applied domains. In recognition of his exceptional research contributions and academic excellence, Professor Rao Liu received a Scholarly Activity Award from the University of South Carolina, Aiken in 2013. Through his continued research, teaching, and service, he has established himself as a respected scholar in graph theory and computer science, making valuable contributions to both disciplines and inspiring students and research worldwide. With this small background, I welcome Professor Liu Li to deliver his talk on the degree-based indices, classical inequalities, and some Hamiltonian properties of that. Professor Lee, now the floor is yours.
Okay. Okay. Thank you, sir, for your kind introduction. First, I would like to thank the organizing committee, particularly Dr. Paul, for inviting me to give a talk in your great conference. So today I will talk about degree-based indices, classical inequalities, and some Hamiltonian property of graphs. First, let me introduce three indices in this talk. The first one is called inverse degree. Suppose G is a graph, and then if we sum up the reciprocal of each non-zero degree, and then this summation is called inverse degree of this graph G. And the second one is called harmonic index of a graph. For the first one, I didn't find the first paper introduce that definition. For this harmonic index, according to the reference, it was introduced by this professor in 1987. This one says for each edge in one graph, and we sum up the degree of the two end vertices for that edge, and take the twice of the reciprocal of that summation, and we sum up this expression for each edge in that graph, and then this summation is called harmonic index for the graph. The next one is called first Z-graph index of our graph. This index was introduced by some chemical graph theorists. So basically, we will find the summation of the square of degrees of all the vertices in one graph. And those are the papers introduce these concepts. And there is several papers about this index. This is a very important index. There are a lot of investigation about this index. In this talk, the so-called Hamiltonian property of one graph really means Hamiltonian graph and traceable graph. The Hamiltonian graph really means if one graph contains a cycle, this cycle contains all the vertices in that graph. So-called traceable graph really means this graph contains a Hamiltonian path, and the so-called Hamiltonian path really the path contains all the vertices in the graph. And I believe if you study graph theory, you know Hamiltonian graph and also traceable graph. They are very important topics in graph theory. Basically, I want to talk about three triple of theorems, and I will give you the proof for one of the three theorems in each of the three triple. And the following 1, 2, 3, 4 theorems played fundamental roles within my proof. The first two appears in this reference proved by Giotto and Urbus in 1973. This one says if the independence number of one graph is less than equal to connectivity, and then we say this it guarantees that this graph is Hamiltonian. And there's a corresponding theory for the traceable graph. This one says if the independence number of one graph is less than the connectivity plus 1, and then this graph is traceable. Really means the graph contains a Hamiltonian path. The following two theorems they will be used within our proof. Particular, we will decide the extremal graph in our theorems. The first one was proved in 1963, appears in this paper. This one says, suppose one graph G is a balanced bipartite graph, and if you pick up one vertex in first part and pick up any index, any vertex in the second part, if summation of degree is greater than n plus 1, and then certainly those two vertices are not adjacent, and then this graph is Hamiltonian. The third one is a little bit complicated, but basically you just remember that if suppose right now I have two connected bipartite graph, if the degree of the vertex in the first part is relatively large, the degree of vertices in the second part also relatively large, okay? And then the so-called the longest cycle for these two connected graphs will be at least this one. Again, lemma 1.3 and 1.4 will be used when we decide the extremal graph in our theory. And this is the reference to this lemma 1.4. So let's see our first main result. Basically, I will use inverse degree, give a sufficient condition for Hamiltonian graph and also a traceable graph. When I prove this one, I will use this classical inequalities, arithmetic mean greater than geometric mean greater than the harmonic mean. And certainly, we assume all the xi here are positive real numbers. And also, remember that if the equality happens, all the xi must be the same. Now, let's see how can we use the first four lemmas plus that inequality to give us sufficient condition for Hamiltonian graph and traceable graph. And the following two results from this paper. This one says inverse degree less than k plus 1 square. Certainly, we assume G is k connected, and we have vertices, E edges, and the maximum degree is capital delta. And if this one inverse degree less than this one, and then we say G is Hamiltonian, or G is complete bipartite graph. And once again, we'll use lemma 3, lemma 1.3, lemma 1.4 to decide the extremal graph for this condition. We have a counterpart for the traceable graph, and the concrete contents for this theorem is here. In this talk, mainly I will talk about the sufficient condition for the Hamiltonian graph, and for the traceable graph, we can prove it in a similar way. Okay, so here is the proof. Suppose we have a G satisfying the condition in theorem 2.1. We prove by connotation, suppose G is not Hamiltonian, and then by lemma 1.1, and then we can see independent number greater than k plus 1. Again, please recall this lemma 1.1, okay? And we also have n greater than 2 delta plus 1 greater than 2 times k plus 1, because the famous Dirac theorems in Hamiltonian graph theory. So this condition implies we can find k vertices in the graph, and then those k vertices from independent set. So next, we'll find the bound for the inverse degree. Before we do that, we have the following observation. Remember, here is the independent set. This one consists of k plus 1 vertices, and this is the graph, and then on the top will be all the remaining vertices in this graph. And certainly, there are some edges between the top part and the bottom part, okay? At the same time, it's possible there are some edges in the top part. And therefore, we have the following trivial observation. Although this observation is trivial, but in the proof play very interesting roles for this inequality. The summation of degree the summation degree of vertices in the bottom part just equal to number of edges between the top part and the bottom part. And this one will be less than the summation of degree of vertices on the top part. And we call the hand-shaking theorems in graph theory. We know summation of top part, summation of degree of the vertices in the top part, and the summation of degree of vertices bottom part and the top part equal to twice of the number of edges, and then we have this inequality. We'll use this inequality when we give the estimate for example, for each vertex in the bottom part, right? Okay, and then this reciprocal is greater than this one because this one is implied by AM of this collection degree greater than HM. And again, if you check the inequality I introduced before, and then we have this one. And I equal to K plus 1. Again, we use this inequality. Summation of this one greater than, less than E, and if you take the reciprocal, will be greater than the reciprocal of E. Okay, so this one. And let's see the, this is the top part, bottom part greater than this one by the classical inequality. And for this one, because each vertex, the degree of each vertex is less than equal to the largest degree. And if you take the reciprocal, we have this one greater than this one. And in total, on the top part, we have n minus k plus 1 vertices. So therefore, this inverse degree is greater than this one, And then after we find the lower bound for this one, we place this case trace, the upper bound case trace for the inverse degree, and then we have this inequality. And then this inequality, this equality implies all the inequality here become equality. And in particular, we have this one, And if you check the proof before, and I want to mention this one. If we have this property, means this graph must be bipartite graph. So this one implies what? On the top part, there are no edges between any two vertices. So this is interesting observation. It will help us to decide the extremal graph in our theorems. Okay, let's continue. And again, based on the AM, GM, HM inequality, we have all those vertices on the bottom part. We have the same degree, and also I already mentioned this one. We have the sum of degree of vertices on the top part. Top part here is equal to sum of degree of vertices on the lower part. And once again, either of those two conditions implies this graph is a bipartite graph. Okay, and then I will skip these technical arguments, and you will see after we realize our graph is bipartite graph, and based on the condition n is at least 2k plus 1, and then we can decide the extremal graph for our theorems. So basically, I will skip a little bit of details here. Okay, and so again, those are the case analysis. Sometimes say we can get a contradiction, and in the last slide you can see we figure out the extremal graph really is complete bipartite graph, and therefore we complete the proof 2.1. 2.2 can be proved in a similar manner, and basically you just revisit my proof for 2.1, use lemma 1.2 replace lemma 1.1, use the condition in theorem 2.2 replace the condition in theorem 2.1, and also when we decide the actual triangle graph for theorem 2.2, and it will be a little bit involved, and at that time we need the combination of lemma 1.3 and lemma 1.4. Once again, I really want to show you the ideas for our theorems. You can find all the technical arguments in my paper. So this is the first two theorems in the first triple. And again, often we want to find the lower bound and upper bound for the indices. And once again, if you revisit the proof of theorem 2.1, and then you can see we can find the lower bound for the inverse degree, and at the same time use pretty similar arguments in theorem 2.1, and we can decide a trimal graph for this lower bound. So once again, I will skip the details, and you can find all of them in my paper. Let's see second one. In the second one, we'll use a harmonic index to give sufficient condition for Hamiltonian graph and the traceable graph. At the same time, we will give a bound for the harmonic index. The key elements for this part is we will use this classical inequality, which we call switcher inequality. This one says, suppose we have a collection of real numbers, and the upper bound and the lower bound for this collection of numbers are M and capital M. And then we have this inequality. And if M equal to N, this inequality becomes equality. If M is really greater than capital M, really greater than smaller m, and then N will be an even number, and half of N, the gamma K will be equal to lower bound. Half of the gamma K will be equal to the upper bound. And once again, this inequality is from this paper, 1914. Okay. Anyway, now next, I will show you how can we use that classical inequality to get sufficient conditions for based on harmonic index for the Hamiltonian graph. So this one says, suppose G is a K-connected graph with n vertices, e edges, minimum degree delta, maximum degree capital delta. And if harmonic index is greater than this expression, and then this one is Hamiltonian. Again, there's a new parameter in this condition. M equal to K plus 1 times delta squared plus E squared divided by N minus K plus 1. Okay, and in the proof, you can see why we have M like this. And once again, we have counterpart theorems for the traceable graph, and here is the concrete contents for the sufficient condition for the traceable graph. Once again, all those the two results here are from my paper here. Okay, and let's see. The structure of the proof is similar to the proof of theorem 2.1. Once again, we assume G is a graph satisfying the condition of our theorem 3.1. Suppose G is not Hamiltonian, and based on this lemma 1.1, we have independent number greater than k plus 1. And once again, by the famous Dirac theorem, and if G is not Hamiltonian, and n must be at least 2 delta plus 1, and greater than 2k plus 1, okay? And once again, because the independence number is greater than or equal to k plus 1, and then we can choose k plus 1 vertices in the graph, and then those vertices from independent set. Now, once again, I use this picture. Let me recall you what I want to get is sum of degree of vertices here is less than or equal to E, number of edges. Sum of degree of vertices here on the top is greater than number of edges. We already used this fact before, okay? So I just repeat a little bit. And then for those n minus k plus 1 vertices, and we apply CBS inequality, of course it's plus inequality, and you can see this one is less than summation of square. Here you can see 1 time this one, and the summation of square. This one is the square of the summation. Square of the summation. Once again, this time we use this observation. Sum of the degree of vertices on the top is greater than number of edges, and therefore we have this one. And certainly this summation is equal to n minus k plus 1, and then divide both sides by n minus k plus 1. We have this one, which means we have the lower bound for the sum of degree of all the vertices appears on the top part. And then we will see this summation. We'll see the sum of the square of all the degree of all the vertices. So here, all the vertices, this one equal to sum of the square of all the vertices on the bottom part. This one, sum of the square of degree of all the vertices on the top part. And we already proved this one greater than this one. Certainly, for each vertices in our graph, the degree of 8 is greater than the minimum degree. And if you recall, the size of I is equal to k plus 1. So therefore, we have this one. So then here really is the reason why we have m here. The expression for m is in this form. Okay? And this one, for any two vertices, the sum of degree of those two vertices greater than 2 times smallest degree, less than 2 times the largest degree. And then we'll apply this switcher inequality. So let's see. Here, this part, we use that inequality. So this one, gamma k. This one, reciprocal of gamma k. And then if you go back to that inequality, 4 times smaller m, capital M. And here, smaller m plus capital M squared. Be careful. In total here, we have E terms, because this summation is ranging over all the edges. So therefore, the number of terms here is E. So then this one is based on that classical inequality. And if you recall the definition of harmonic index, this one equal to half of the harmonic index. Now, this is another important fact in graph theory. And this one say you take any edge, you find the summation of the degree for two end vertices. This one equal to this one. If you are familiar, this one that is trivial for you. If this one is new for you, you should think about it for a while. But again, not very hard to understand. And then we already proved this one. And then this one will be greater than m. This one is a condition. So half of harmonic index greater than this one. And then we change this one to this form. Why we choose this form? Because we know this upper bound. Once again, we force all the inequality here become equalities. And therefore, we can decide the extremal graphs in our theory. Okay? And once again, when those inequality become equality, we have something like this. And if you go back to the very classical theorems, and we will have those conditions. And once again, I try to avoid technical details here, and basically pretty easy for you to prove that we have, for this one, we don't have extremal inequality, which means if we have some extremal graph, okay, we'll get a contradiction. We don't have extremal graph, I'm sorry, okay? And certainly based on the that classical inequality, we classify the technical part into different cases. Once again, we complete the proof of theorem 3.1, okay? And again, 3.2 can be proved similarly, and again, use the lemma 1.2, replace lemma 1.1, use the condition of theorem 3.2, replace the condition 3.1, okay? Because this one, we don't have extremal graphs. So if you mimic the proof in theorem 3.1, you can easily prove theorem 3.2. Once again, we have byproduct, and if you revisit the proof of theorem 3.1, you can find the upper bound for the harmonic index. Once again, because for all the indices, you cannot find the close mathematical expression. And if we cannot do that, we want to find either lower bound or upper bound for those indices. Last one, okay. We will use polycycle inequality to give a new sufficient condition for Hamiltonian graph and traceable graph. And this polycycle inequality is one of the reverse CBS inequality. In fact, there are other reverse CBS inequality. This one says, and remember, for the CBS inequality, this one should be less than this one. Okay, reverse really means right now with some actual condition, I can use this one bound this one. And here the actual condition. We have real number AK, BK, lower bound AK, M1, capital M1, lower bound, the bound of BK, M2, capital M2, and then we have this inequality. Once again, if this condition is true, this inequality become equality. If this one greater than this one, there are some conditions, and then we can decide the special numbers for AK and BK. The detail is here. Once again, we'll use this part to decide the extremal graph in our theory. Once again, these theorems appears first here. Okay, here are the theorems I intend to prove. Suppose G is a K-kinetic graph, E edges, minimum degree, maximum degree, and the first Z-graph index, I use M1 to represent it. And this one say if M1 is greater than this one, and then this graph is Hamiltonian. Or G is a complete biparallel. We have similar theorems for the traceable graphs. Again, those two theorems appear in my paper here. Okay, once again, the initial part for the proof theorem 4.1, the same as before. The key is we can find K plus 1 vertices, and those vertices form an independent set. Repeat this part, repeat the one we had before. Finally, we have this inequality. And combine this identity, we have this one. We'll use the observation here in our proof. So how can we apply polynomial inequality? We'll apply that inequality for the K plus 1 degree, the degree of K plus 1 vertices. Again, those UI appear at the bottom part. And this one is trivial. For each vertex here, in the bottom part, greater than or equal to smaller degree, but bound by the total number of vertices on the top part. In the top part, we have n minus k minus 1 vertices. Okay, so and then we can consider use that polynomial inequality with AI equal to 1, BI equal to BOI, and then this is the right hand side of the polynomial inequality. Once again, we use this observation, summation of those guys less than E, and so that we can get the upper bound for this one here. And over here we have K plus 1, once K plus 1 terms, and then divide by K plus 1. Okay, and then you can see this is definition of first Z-graph index, and for this part, all the weight appear on the top part, and each B weight less than the largest degree. On the top part, we have n minus k minus 1 vertices. So this one, we already obtained this one here. And here is the condition. Once again, because of this upper bound, and then we can figure out this condition. And that will force all the inequalities appear before become equalities. Okay, and then we have something like this. And based on, once again, for the polynomial inequality, and then we divide our remaining proof into the two cases. One is delta equal to n minus k minus 1. Really means that M1 times M2 equal to capital M1 times capital M2. Okay, and once again, at the same time, we use the lemma 1.3, and then we can decide the extremal graph. This is the first case. And second case, this one really corresponding to M1 times M2, less than strictly capital M1 times capital M2. And maybe this one a little bit involved, but also not very difficult. And you can see eventually we get a contradiction, which means this case cannot happen. And therefore, we completed the decided the extremal graphs and then completed the proof for this theorem 4.1. And 4.2 can be similar proof. And when we decided the extremal graph for theorem 4.2, we need to combine lemma 1.3 and lemma 1.3. And once again, a little bit technical, but can be easily handled. Once again, similar to the earlier cases, and we can find the upper bound of the first Zygarb index. And so basically, if you revisit the proof of theorem 4.1, you can easily find this upper bound, okay? As for the extremal graphs, when we decide extremal graph, it's a little bit involved, but also can be handled. So I will skip the details here. Basically, we have two types of extremal graph. And once again, if you are really interested in it, check my paper. Okay. Finally, I want to make some comments and use the ideas we approve theorem 4.1, 2.1, 3.1, okay, and combine with other classical inequalities. Particular, there are several converse of the CBS inequalities, and then we can find a lot of new conditions for the Hamiltonian graph or traceable graph. And here, some of them I completed in the last 2 years. And once again, if you are interested in it, you can find all those papers. I believe all those papers are online papers. And I think that's all for my talk. Thank you so much.
Thank you, Professor Liu. It was very excellent talk given. And let me ask the other participants, if you have any questions, you can ask Professor Lee. Participants, you can raise your questions now. Professor, I have a few questions.
Sure.
Yeah. In your talk, the degree-based indices, everywhere you have discussed about the Zagreb index with the Hamiltonian properties.
Yeah.
Okay. Instead of Zagreb index, can we go for the Wiener index or some other indices based on degree-based?
Yes, there are a lot. In fact, there are a lot. Okay. I think first you can use the proof strategy here. I just talk to get new sufficient condition for the Hamiltonian graph. For example, okay, one of them is called a generalized first Zygarb index, which means that du square you change it to du alpha. Okay, alpha is let's say any real number greater than or equal to 1. Or you can define another one. It's called generalized inverse degree. Inverse degree 1 over du, right? Okay, you can change that one to 1 over du raised to power alpha, and then you can get a new result. And also, you can figure out the new strategy. Okay, in fact, I have some papers and generalized ABC index, generalized APC index, and so on and so forth. Okay, and you don't need to use classical inequalities, and you adopt other proof strategies, and then you can use other indices to find a new sufficient condition for Hamiltonian graph or traceable graph. Maybe some additional property of a graph. Often I limit my research to Hamiltonian